Alright, let's go with it here. So, this is 4.1. This is the lecture for 4.1, and it's just basic graphs. So this is a review lesson, those that didn't were absent on that day here. So first things first is we're going to try to go from the unit circle onto a regular graph. So we're going to go from here, and we want to go to here. That's the whole goal. From unit circle to the rectangular coordinate system. So first things first is we don't want to do degrees because that's useless. Degrees are rotations of a circle, so there's no point to even look at these guys here. So degrees are gone for us. Okay, so the other angle measurement we know of would be radian measurements. So in this case, that's kind of cool because those guys are actually real numbers. They look funny, but like pi over 2 is roughly 1.57, and that's a real number. 1.57 is approximately, right, 1.5. So those are real numbers. So first things what we're going to do is we're going to try to do a graph of the sine function. That's the first thing we want to do. And if you want to, you can put them in columns. You can put them in, but really roughly, I'm going to show you an applet in just a little bit here. But so we want to label this. Let's look at the x-axis. Our x-axis are going to be our radian measurement. Our y-axis is going to be the height. So first things first is notice the height for a sine curve. The highest it'll go is actually 1. The lowest it'll go is -1. So that's going to be our bounds. Second thing we got to think about is angle measurements. So let's do this here. All the way around the unit circle. If you went all the way around the unit circle, you go from 0 to 2 pi. Right. You got 0 to 2 pi, and my pen is failing me here. Let's see. Let's see this. There it is. Grab another pen. Oh, much better. Okay. 0 to 2 pi. So what we're going to do is we're going to label the highest we're going to go out is 2 pi. And so this is kind of like unraveling a unit circle here. And so that means half of that would be pi. Half of that would be pi over 2. Then half of that would be even a pi over 4. So now what we want to do is we kind of want to fill in. So we start here, pi over 4. As we add another pi over 4, this would be like 2 pi over 4, right? 2 pi over 4. This would be 3 pi over 4. This is 4 pi over 4. And then we're going to kind of cut these into different pieces here. So between pi and 2 pi is going to be a 3 pi over 2. That's the middle between the two. And if you want to see it on a graph here, the middle between this guy and 2 pi is 3 pi over 2. So now we're going to grab this one. There's my 5 pi over 4. And there's my 7 pi over 4. And that is pretty good because I got a good idea of where those things are. But we are going to fill in our graph even more. So now let's go with pi over 6. And notice pi over 6 is kind of close. It's not in the middle. It's not between pi over 4 and 0. It's a 30-degree angle, right, versus a 45-degree angle. So kind of be mindful of that, and the fact that it's not a 22-degree angle, 22.5-degree angle. So 30, pi over 6 would be about right there, kind of more of the way to pi over 4. Okay, and pi over 3, which would be a little bit past that. So it'd be about right there. So I got those. Let's keep on going. So if we start looking at this area here, that's the next one we want to kind of put down. We have the 3 pi over 4. So the 2 pi over 3 is going to be about there. 5 pi over 6 is going to be about right there. Alright, doing this side now. So this will be 7 pi over 6. This will be 4 pi over 3, or representing the 240 degree angle. I know it's kind of getting a little messy here. So then let's just finish up here with these ones right here. So we got the 7 pi over 4, the one closest to it, but before it would be a 5 pi over 3. The one afterwards would be an 11 pi over 6. Okay, now we are pretty good here. Let me start erasing a lot of stuff here, just so don't get cluttered. Okay, so now all we're going to do is we're going to graph sine curve. And since we're graphing sine curve, remember the y value is your sine of x. So all we're going to do is we're going to graph. Let's put in maybe like 1/2 over here, negative 1/2 over here. So at pi over 6, actually no, let's go back to 0. At 0, the y value is 0, so we're going to put a dot right there. At pi over 6, the value is going to be 1/2, so here we're going to put it right there. That's a half. At pi over 4, it's going to be square root of 2 over 2. So on your calculator, just real quick here, calculate for me the square root of 2 divided by 2. And it should come out to be a 0.707. So at pi over 4, it's about right there. Then at pi over 3, we want to calculate square root of 3 over 2. So punch in the calculator, square root of 3 over 2 gives you and should be 0.866. I think that's the 0.866. So 0.9 roughly. And so we go over here, it's about right there. Alright, at 2 pi, or pi over 2, sorry, it is 1. So that one's going to go all the way over here. And pi over 3 should have been about right there. Didn't graph it there. Okay, so that's how we're forming our sine function. And we go around and around and around. So let's go with it. Y value at 3 pi over 2. Hey, notice they're exactly the same as this one right here, right? So in this case, it's going to be so you got to kind of know these. So square root of 3 over 2 is going to be about a 0.9 for us. The square root of 2 over 2 is going to be about a 0.7 on our graph. And then we just keep on going. So at 2 pi over 3, we're going to graph 0.9. At 3 pi over 2, we're going to graph a 0.7. At pi over 6, we're going to graph a 0.5. And then at pi, the y value is 0. So that is how we put together the sine function. Have to do it for sine, we'll have to do it for cosine, and so we'll do all 6 of them. So let's just kind of hurry up on this one here. So at 7 pi over 6, it goes underneath. Now it goes to a negative 0.5. At 5 pi over 4, a negative 0.7. 4 pi over 3, a negative 0.9. And at 3 pi over 2, probably a little tiny bit lower here. Yeah, we hit ourselves our negative 1, which is our minimum value. And then it starts climbing back up. 5 pi over 3, we have ourselves a 0.9. Then a 0.7, then a 0.5, and then at 2 pi, it's 0 again. So let's start now connecting the dots together. And we connect the dots together, voila. What happens is we have taken the sine curve out of the unit circle and we've put it onto the rectangular coordinate system. Now, quick question. Does it keep on going? Can it go past 160 degrees or past 2 pi? Absolutely. So this thing will keep going. Some trig books, they actually make the students put a little arrow at the end, and then make an arrow right here. They'll say, hey, look, just so you know, it's going to curve both ways forever and ever and ever. So that's the sine function. Okay, guess what? We've got to do the cosine function, the tangent function. Okay, here we go. Cosecant, secant, cotangent. There it is. That's what we have to do here. And this is going to be, again, this is just getting the basic graphs. And then 4.2, 4.3, we start changing them around. You know, making the height bigger, making a vertical shifts and all that stuff. Okay, so let me erase all this, and now we're going to start with the cosine function. We're going to go a little faster, obviously, because we already done a whole bunch of this work prior. And then the other thing that we got to do is something called odd functions and even functions. So we have to know that sort of distinction there too. So let me erase everything. Before we go on to the cosine function, I just want to show you just a graphic of how the sine function is going to be graphed. So here's a unit circle. This is a connection from unit circle onto the graph itself. So we're at 0. This is in terms of degrees. So you kind of see how this works here. So at 30 degrees, notice it's the connection from 0 here going up. Then we go up to 45 degrees. This is when it's root 2 over 2 or 0.7. Then we hit 60 degrees. Right, and then eventually we're going to hit the 90-degree mark. And notice what happens here. There it is. So that's how we change from sine and cosine. It's really, this is a cool graphic because it shows you that little height, the height of the y value changing, and we're just kind of plotting it as we go over here. And then so we go, and then it starts going down, 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 down until it gets to 180. Then it hits the 0 marker, and then it keeps on going down even further, right, until it hits the, let's see, that'd be 270 or 3 pi over 2. And then it goes back up to the top at 2 pi. So there it is. I just figured that's a really neat graphic to show how we go from unit circle onto the x and y coordinate system. Back to beginning here. So we have ourselves 4.1 basic graphs. And let's do cosine. Cosine of x, or cosine of theta. So let's, this one's a little bit more interesting. We're going to look at the cosine values. So this is going to be the x values. So if you kind of want to, what we're really doing is we're doing this, really. We're taking the angle values and we're making them to be x and y graph. And those angle values are in radian measurement. Okay, so let's go with it here. So 2 pi, again, same exact process. We're going to go pi. Hopefully my pen doesn't give out. Pi over 2, pi over 4, and very similar to what we had before, 3 pi over 4. Half, or between pi and 2 pi is 3 pi over 2. Half of that would be a 5 pi over 4. Sorry, in between pi and 3 pi over 2. And then this one would be a 7 pi over 4. Okay, now we're going to fill in the other pieces here. You know what, I'm not even going to give you the, we should here. So this is pi over 6, pi over 3. Then around 3 pi over 2, this is 2 pi over 3. This is 5 pi over 6. Around 5 pi over 4, it is 7 pi over 6, 4 pi over 3, and around the 7 pi over 4, the values we know are 5 pi over 3 and 11 pi over 6. There it is. Okay, so now we are looking at the x coordinates. So we're kind of looking at this line right here. And at 0 radians, the value is actually 1. So now this is -1. We can label ourselves a -1/2. We can label ourselves a +1/2. Boom, let's go with it here. So for cosine, interestingly enough, the cosine, it starts off at 1. For pi over 6, now we have ourselves at √3/2. And hopefully remember √3/2, punch it in the calculator. Square root of 3 divided by 2 should give you 0.866, or just 0.9. So now we start off here. 5 pi over 4, the x coordinate is square root of 2/2, which is a 0.7. Add pi over 3, it's 1/2, so 0.5. Add pi over 2, now the x coordinate is 0, so we have ourselves that. 2 pi over 3, the x coordinate, which is this one, goes to a -1/2. -0.7, -0.9, and at pi it becomes a -1. So there's pi. So let's keep on going. Then we have ourselves a -0.7. Oh, sorry, 0.9, sorry. 0.7, 0.5, and we're back at 0 when we hit 3 pi over 2. Alright, let's keep on going. Almost done here. So this is 0.5 now. So it jumps to 0.5. At 7 pi over 4, it jumps to 0.7. At 11 pi over 6, it jumps to 0.9. And right at 2 pi, we're back up to 1. So, okay, this is the cosine curve. Let's connect the dots together now. So that is our cosine curve. And it's all about the x coordinates. Okay, tangent coordinates, not so fun. So sine and cosine, they are used quite a bit to model things that go back and forth in nature. And those are easy to graph because you're just taking either the y coordinate or the x coordinate. All right. The tangent function is a little more difficult because now you have to calculate things. Now you have to calculate the ratio of y over x, and that one will need a table to do that well. All right. So let's start using a table. So there's sine and cosine. So there's your basic graphs here. We've taken cosine off the unit circle. Awesome. And we've made it into a basic x and y coordinate graph, which is super cool. Okay. So now let's move on to tangent. Tangent, again, a little tricky. So now let's make ourselves tables just so we can keep track of stuff. So this is going to be kind of long as we put things together here. So I'm going to say that this is my this is going to be my angle measurement. This is going to be my y coordinate, my x coordinate, and this will be the tangent function, or y divided by x. That's what I really need to get to. So now the question is, what does a tangent function look like? All right, so we got 0. We have pi over 6, and we're going to be here for a while here. pi over 4, pi over 3, pi over 2. Now it's 2 pi over 3, and you're looking back at your unit circle. If you have a unit circle with you, back of your textbook, just keep on looking at that unit circle. Let's get all the angle measurements here. Alright, next one is 3 pi over 4, 5 pi over 6, then we have ourselves pi, then we have ourselves 7 pi over 6 off the unit circle. This is where I'm getting it from. I'm just looking at the back of the textbook, getting the unit circles off of this here. 5 pi over 4, 4 pi over 3, 3 pi over 2, almost done, almost done. 5 pi over 3, 7 pi over 4, 11 pi over 6, and voila. Let's see if I can put that in there. There it is. 2 pi. Okay. Whew. Okay, let's see if I can go a little bit faster here. So for the y values, we're going to fill in the cosine values, then we're going to fill in the ratios of y over x. Let's go with it here. So 0, this should be quick because remember everything's a pattern, right? Then it starts coming back down. Then we go into the negatives. We hit -1, and we start climbing back up to 0. There it is. Alright, the x values are the exact opposite. Alright, so they start off at 1, and we start going down. Root 3 over 2, root 2 over 2, 1 over 2, 0. We go into the negatives. -1/2, negative root 2 over 2, negative root 3 over 2, -1, and then we start climbing back up. And when we get to 0, we keep on going higher and higher. 1/2, root 2 over 2, root 3 over 2, and eventually back up to 1. Okay, so now for the tangent function. So we're gonna graph this guy. We need the ratios of y over x. In this case, it's 0 over 1 would just be 0. Now this would be 1/2 divided by root 3 over 2. That doesn't look nice. It's 1 over root 2, 1 over root 3. And just punch that into your calculator. I'm going to have to do that too here. Divided by square root of 3. There it is. It's about a point. It's 0.577, so 0.6. Okay, this was the funny one. It's going to be root 2 over 2 divided by root 2 over 2, which is 1. And then we'll develop the pattern here in just a bit here. Last one would be that we really need to compute here. It's going to be root square root 3 over 2 divided by 1/2, so the denominators cancel, and we're just left with root 3. And root 3, punch it in on a calculator as well, just so we know what that is, 1.7. Alright, this one's going to be 1 over 0, which will just give us undefined. Our tangent is not defined at pi over 2. Alright, so we know the pattern is going to continue. So, it's going to be a negative 1.7. It'll be a negative 1, negative 0.6. It'll go up to 0 again. Positive. If you divide these numbers out again, it'll be a positive 0.6, positive 1, positive 1.7, then it's going to go to undefined again. And starts off again at negative 1.7, negative 1, negative 0.6, and back to 0. Okay, that tangent function is a little different there. So can we graph these points? We're going to go to 2 pi again. And there's pi. Pi over 2, pi over 4. Three pi over 2. The middle of these guys would be 3 pi over 2. Sorry. This guy's 3 pi over 4. There it is. Okay, between here is a 5 pi over 4. In between there, exactly in the middle, is a 7 pi over 4. Okay, so just so this thing does not get too clogged up, the 0.6 and the 0.3, we're going to guesstimate them as we go. Okay, tangent function. Let's see how this begins, and let's make this get to be a 1 here, a negative 1 there. And so it starts off at 0. By the time it reaches pi over 6, which is about right here, it's actually 0.6. At pi over 4, it goes up to 1. Hey, and at pi over 3, which is about right there, it's actually a 0.7. So it's that, if that's 1, 2 is all the way up here. It's actually up here. And then what happens at pi over 2, it's undefined. So the way we say undefined in algebra, hopefully you guys did this as well, you make these little dashed lines coming straight down, saying, well, there's going to be a break in my graph. So the question is, what does this tangent function look like? Where does it go? How does it actually never reach pi over 2? And so as we start connecting the pieces, let's at least connect this piece together. Then we notice, what's happening here? It's going like this. Not a very nice curve there. It's going to go like this. It goes off to infinity as it gets closer and closer to pi over 2. Then what happens if we're going to go a little bit beyond pi over 2 at 2 pi over 3, which is about right here, we're all the way down here again. So there's my negative 1.7. There's my negative 1. Here's going to be my 0.6. And at pi it's 0, and it starts all over again. Here's my 0.6. At 5 pi over 4, it's a 1. At 4 pi over 3, it's a 0.7 again. And at 3 pi over 2, it is undefined. So now we kind of see what's happening here. It's coming from the bottom, because it's undefined. It's making this little bend like this. And it's curving out again to do the same exact thing. As we go beyond 3 pi over 2, at 5 pi over 3, here it is all over again. negative 1.7, negative 1 at 7 pi over 4, at 11 pi over 6, it's a 0.6, and we get ourselves back to 1 over here. So let me adjust this little dot just a little bit here. There it is. So here it is coming through. Alright, there is our tangent function, our basic tangent function. Alright, we got 3 more to go. So now let's look at the reciprocal functions of each one of these. Alright, the rest of the video looks like it did not record when I did it here, so I'm just going to show you as you go. In fact, let me put it on laser to show you what's happening here as we go, and just fill out the markers as you go. You'll see actually all this here, but let me with the laser pointer sort of guide you through what is happening here. So we are going to graph cosecant x. That's the first one. You already see what's going to happen with the graph itself here, so you can go ahead of me if you like, but we start off with cosecant is really the y coordinate or the reciprocal of the y coordinate. So we have to make ourselves our little table again, which I filled out already here. And so whenever you have a 0, the reciprocal of 0 is going to be undefined, so we can fill those out right away. So at 0 it's undefined. Find any other zeros here as we're making our table. That's an undefined. And then all the way in the bottom here, there's your undefined as well. So we got 3 undefined terms here. And with the undefined terms, you know there's going to be a break in our graph. That's kind of what you're looking at. Alright, so let's go with it here. So cosecant reciprocal of sine. And so you're going to take that little 1/2, take the reciprocal, get a 2 out of it. Square root of 2 over 2. When you do the reciprocal there, let me write that one on the screen real quick here just so we see it, and then we'll do the pattern here. It's going to be, if you take a reciprocal of 2 over 2, so take the reciprocal of it, becomes this, and then when you rationalize your denominator, you wind up having 2 root 2 over 2. The 2's cancel, and you're still left with a root 2. So that root 2 turns into a 1.4. Taking the reciprocal of root 3 over 2, which would be 2 over root 3. If you punch it in a calculator, because that's what you want, because you're graphing, it turns out to be a 1.15 or close to 1.2. Reciprocal of 1 is 1. And then the pattern starts all over again. So once you see a root 3 over 2, reciprocal becomes a 1.15 or 1.2. See a root 2 over 2 becomes 1.4. 1/2 becomes a 2. We already did the 0. So if you see a negative 1/2 becomes a negative 2. And the pattern continues, negative 1.4. And I'm going to just approximate 1.15 as 1.2 from here on out. So negative 1.2, negative 1, negative 1.2, negative 1.4, negative 2, and we're done. So there's filled out our table really quick. Pause the video if you need to fill out the table. Alright, we're going to do what we did before. We're going to stretch out a graph right here, y-axis, stretching from the highest value we have is 2. So I'm going to put a 2 here. I'm going to go down to negative 2. I'm going to stretch out the x-axis all the way to 2 pi. Take half of that, which would be pi. Take half of that would be pi over 2. Take half of that would be pi over 4. And then you fill it in. So pi over 4. This is technically like a 2 pi over 4. Then you fill in a 3 pi over 4. This is technically a 4 pi over 4. Don't need to write it, we already have it. 5 pi over 4. 6 pi over 4, same thing as 3 pi over 2, and 7 pi over 4. There's our little tick marks that we've developed. Okay, so we have those, so you should have those. And then we start graphing. So then we say, let's fill in all our undefined phases first. So you're going to put a dashed line all the way down at 0 marker, at the pi marker, and at the 2 pi marker. Those are going to be all filled out. And then we start putting in our points. So at pi over 6, and we're going to put this little dashed line. It's kind of close to pi over 4, but not all the way. So it's kind of like 2/3 of the way to pi over 4. So put a dash mark here, and the point here is 2. At point 4, the value is 1.2. That's 1.4. Sorry, well, that's 1.4. A little bit away from point 4 is, or pi over 4 is pi over 3, which is that 1.2 value. And at pi over 2, we should put a marker at right at 1. Alright, next one. 2 pi over 3 right here. This is 1.2. Moves up to 1.4. Moves up to 2. And then we have our break. So question is, with these dots there, what's the graph going to look like? And I already drew it over here for you. But the graph looks like a little horseshoe. Arrows at the end. Then we move beyond. Pi. So we're moving beyond this undefined term. So we start off at -2, and then we do this little pattern here. So it looks like it's all of them. It's kind of like a repeating pattern of the positive ones, but in the negative value. So -2. At 5 pi over 4, it's -1.4. 4 pi over 3 gets you a -1.2. 3 pi over 2 gets you a -1. And then at 5 pi over 3, make a little small tick mark here, -1.2. A tick mark that's close. This is right here, so that's going to give us that value. And 7 pi over 4 is a 1.4. And that one's going to give us a -2, and we go. There it is. So we have values like this. Again, horseshoe on the bottom side, right? On the inside. So there's our cosecant function. That's what it looks like based upon our table, based upon our values. Jumping to the next one. This is the secant function. And what I did is all the stuff in red is from the previous one, all the stuff in blue. Now I made another column, so columns would be moving too far to the right, so I'm erasing that column, setting it up again here. So cosecant function now is the reciprocal of cosine right here. So that means we're taking reciprocals of the x values, so instead of the y values. So same exact process, same exact everything here. So let's go through and let's get rid of all the undefined ones. So 0, reciprocal 0 is undefined, and we can put that in. So we have an undefined term at pi over 2. We have another undefined term at 3 pi over 2. There it is. Okay, going back up, let's go with it here. And you're going to see the same numbers repeat themselves. So 1 reciprocal 1 is 1. Reciprocal root 3 over 2 is a 1.2 from last time. Reciprocal of root 3 over 2 is a 1.4. Reciprocal 1/2 is a 2. And you can kind of see the pattern repeating itself then. So reciprocal there. Now it's a negative value. Reciprocal there. And filling in the table as I go. Pause the video if I'm going a little bit too fast. And we're going to use these as our points. We did this one already here, so now it jumps to the positive side again. So positive 2, positive 1.4, positive 1.2, and then 1. So we're going to finish off at 1. Alright, so let's make a graph. Again, the y piece here, the highest value is 2, so I'm going to put 2 here, a -2 down there. I'm going to stretch this out all the way to 2 pi. Take half of that would give us pi. Then I'm going to take half of that would give us 2 pi over 2. And then half of that would give me pi over 4, and I'm going to fill in the rest here. So pi over 4, this will be 2 pi over 4, this will be 3 pi over 4. I got to write that one in. 4 pi over 4 I already have. 5 pi over 4, I got to write that in. 6 pi over 4, that's the equivalent. 7 pi over 4, let's put a tick mark, write that in, and then we have 2 pi. Okay, with that said, start filling in the dots, and we should get a graph that looks already just like that here. So let's put our undefined terms there. Undefined term coming through. Undefined term at 3 pi over 2 coming through as a dashed vertical line. And then we go with it here. So we're going to graph this little guy at 1. And at pi over 6, which is kind of close to pi over 4, we're going to graph this guy at 1.2. At pi over 4 at 1.4. At pi over 3, we're going to graph at 2, and then at that point it stops, right? Because there's no other dots up till or pi over 2. So as we connect them, we know we're going to have a break in our graph, and there's my graph right there. Start going the other way here. We start off with dots at -2. Start with negative 1.4, negative 1.2, negative 1, negative 1.2, negative 1.4, and negative 2. So we should have these little dots based upon our table. Connecting these dots together leads us into a downward horseshoe, arrows at the end, and there's our break in our graph. If you go beyond pi over 3, our dots are at 2, 1.4, 1.2, and 1. And at that point you are connecting those dots together. So there it is. There's our graph for secant. Alright, one more to go. Cotangent. Again, starting off our graph, and you'll see the numbers repeat the same numbers that we had for tangent. They're going to repeat themselves in different ratios here. So the best way to think about it here, I know you see the graph already, but cotangent of x is equal to cosine of x on top, sine of x on the bottom. That's how we distinguish it, right? That's the ratio identities. So that means we're going to be looking at the ratio of the x coordinate to the y coordinate. So x divided by y this time. And let's start making our table. Here it is, our next table to be made. X over y this time. And what we want to do is we want to figure out where are times where this is undefined. It's going to be undefined whenever the y value is 0. So we can put those in already. So the y value is 0 here, undefined at 0. Next time scrolling down, it's at pi. So at pi, this guy should be undefined. And the only other time is at 2 pi. So 2 pi, this guy is undefined. So let's fill in our undefined terms already. That's done. That's done. That's done. We haven't got to the graph yet, so pretend it does not exist there. So on your calculator, however you want to do it here, the way we did it for tangent, so it's going to be 1/2 divided by root 3 over 2. 2's cancel. Let me show you that. Maybe that'll be easier to show. This would be 1/2 divided by root 3 over 2. You could punch this on the calculator already, or if you just want to get rid of the 2's there, at that point that's what you're punching into the calculator. So 1 divided by root 3 gives you a 1.7. Alright, and then root 2 over 2 divided by root 2 over 2, that's going to be the same thing. The 2's cancel, the root 2's cancel, left with a 1. And the other one, it's going to be root 3 over 2 divided by 1/2. The 2's cancel. You're left with a root 3 over 1, which is just root 3. Punch that in the calculator, and you should get 1.73 or 1.7 for graphing purposes. Alright, let me clear this real quickly here so it's not going to be messy when we're going to be doing the graph. Alright, so 1.7, then a 1, then a 0.6. So this one right here corresponds to the root 3 over 2 over 1/2, just so we're not confused. Right, this one here is going to correspond to 1/2 on top, root 3 over 2 on the bottom, so that's going to be 1 divided by root 3, which is about 0.6 on the calculator. Alright, and the rest we go. So 0 will be a negative 0.6, negative 1, negative 1.7, undefined 1.7, then a 1, then a 0.6, just by looking at the ratios there. 0, negative 1.6, negative 1, negative 1.7. So take the time to fill in the chart, make sure you know where the numbers are coming from, and let's build our graph. Pause the video if you need to. Alright, so we're going to make a graph. Highest point to be a 2, lowest point to be a negative 2. Coming across here, we're going to fill it in with 2 pi at the end. Take half of that initially, gets you to pi. Take half of that, gets you to pi over 2. And then take half of that, gets you pi over 4. And then we have the one that's not filled in. This is pi over 4. This would be 2 pi over 4. Got that? This would be 3 pi over 4. 4 pi over 4. 5 pi over 4. 6 pi over 4, or 3 pi over 2. 7 pi over 4, and 8 pi over 4, which is 2 pi. So there's my x values. And let's go with it. So at pi over 6, which is just kind of close to pi over 4, but not all the way, it's at 1.7. At pi over 4, it's at 1 now. Pi over 3, it's at 0.6. And when we hit pi over 2, it's at 0. And now we progress to the negatives. So negative 0.6, negative 1, negative 1.7, and there's our break. So we have to figure out, okay, based upon these dots, we have this little graph that goes down. And then notice it starts all over again. So the pattern is the same. 1.7, 1, 0.6, 0, negative 0.6, negative 1, negative 1.7. And so in this case, cotangent repeats itself twice. Alright, that was really quick here. The graph was already there, so hopefully you have a good grasp of it there, and pause the video when you need to. Alright, the other thing we got to do is something called even and odd functions. Again, it's already written out. So let me kind of guide you through this process here. So this, pretend it's a blank slate here. Let me guide you as we go through it. So first is even and odd functions. What does that mean? So let's write down even function. Even function. And then we have odd function. Okay, let's talk about the even function first here. Alright, the best example of even function is a parabola. So f of x equals x squared. That is the best example of an even function for us. And if we want to graph it, let's graph it real quickly here. Let's put a y-axis down real quick, an x-axis down. And the parabola goes like this, right? It goes down, hits the 0, 0 marker, and it climbs back up. That's what we say with the even number with arrows on each side. Okay, example of even function. Let's see it. So what happens with the even function is this. If you were to plug in a negative 4 into your function, you get yourself a 16. So f of negative 4 equals negative 4 being squared and gets you a positive 16. If you were to graph a positive, the exact opposite side here, if you graph a positive 4 and you plugged it in, it gets you the same value. So f of 4, which will be 4 squared, would give you a 16. So notice these two values are exactly the same. And so if we want to write it, we write this. F of negative 4 would cause the same exact answer as f of positive 4. In an abstract way, if we kind of do the abstract way, let's do the abstract way. So if you say f of negative x plugged in, and negative x times a negative x would give you a positive x squared. So notice how the negative sign just disappears. And so the way we write it, we say f of negative x will give you the exact value as f of positive x. The negative sign disappears in this case. Graphically, what happens here with even functions is they are symmetric. Symmetric along the x-axis. So if you have this little blue line here, right, if you were to fold it right along the x-axis, fold on top of each other, this line here and this line here would fold right on top of each other. Okay, that's the even function. Even function, because the way it's made, it's symmetric about the y-axis, the negative sign disappears from the function. Okay, put a big bar line down. And let's take a look at the odd function. The odd function is a little different. So let's do an example here. So let's make a graph real quick here. Best example of an odd function is x to the third power. So f of x equals to x to the third. I'll give you the graph of it if you forgot it from algebra. It starts low. It kind of starts curving here when it hits the origin, and then it starts curving back out again. So here's my x to the third function. Alright, let's do an example here. So what happens if you were to plug in a 2 and a positive 2? A positive 2 and a negative 2 into this. So plugging in a positive 2 into this function, f of 2 gets you 2 to the third power, which gives you an 8, right? 2 times 2 times 2. But plugging in a negative 2 into the function gets you a negative 2 times negative 2 times negative 2, or a negative 8. So notice there is a connection here. These numbers are exactly the same, except they're just opposites of each other. So let's see if we can kind of put this together a little more abstractly here. So if I plug in a negative 2 into my function, it's the same thing as plugging in the negative of the positive value, right? So for f of negative 2, I'm going to give myself a negative 8. But the negative of a positive 2 would give me the negative of an 8, which will then be the same. Okay, abstractly, let's look at the abstract list here. So f of negative x will give you a negative x to the third, or negative times a negative times a negative would give you a negative, and negative x times negative x times negative x will give you then a negative x cubed. Alright, how do we do this? I don't know what that n is doing there. That's something from somewhere else. But here it is. F of negative x will equal a negative of f of x. So notice here, in order to change the input to a positive value, we have to stick a negative out in front. And those guys are odd functions. So even and odd. Even, the negative can disappear on us. Does not change the value. Odd functions, we have to, if we're going to make the inside value, the input value negative, we have to put a negative on the outside. Alright, how does this apply to trig functions? Let's go for it. For trig functions here, let's say this. Let's say you make yourself a unit circle, big unit circle. And then you're going to make yourself a positive theta. So a theta going counterclockwise. R value is 1, and we get ourselves a point. So let's concentrate on the positive value first here. So positive theta, R value is 1. I get myself an x and y coordinate system. And because it is on a unit circle, my x coordinate is cosine, my y coordinate is sine. Cool, okay, let's graph the negative value here. So how about the negative angle value? Negative angle value here is negative theta, still a 1, gets me this little corner. And this one's going to give me an x coordinate and a negative y coordinate because I'm in quadrant 4. That corresponds to a cosine of a negative angle and sine of a negative angle. So now the question is this: how do I go from a negative angle to a positive angle? And see, do I get to drop my minus sign, or do I have to stick it out in front? So let's go for it here. So if I say sine of negative theta, that's this over here. And it's kind of funny how it flows here. Let's see how it flows. So from here, we say if that is the case, then that means it's the same thing as this one right here. So sine of negative theta is the same thing as the negative y value in quadrant 4, but really, isn't it the same thing as the negation of the y value in quadrant 1? So it goes from here to here. It's the y value, positive value, with a negative in front of it. So that means it's just a sine theta with a negative in front of it. So it goes negative y becomes a negative of sine theta. So question, did the negative values just disappear? The negative input value of theta disappear, or did we have to stick a negative on the outside? And yes, it corresponds to this. F of negative x is the same thing as negative of f of positive x. The sine is an odd function. So if we were to get rid of a negative angle value and make it a positive angle, we'll always have to stick a little negative out in front. Alright, cosine. Let's do cosine. Cosine of negative theta. So from here corresponds to the x value here. And the funny thing is, because quadrant 1 and quadrant 4, they both have positive x values. So that means this is here. X values are the same. And therefore, cosine of theta is here. Even function, is that right? Notice you have a negative value, angle value, and we can drop the negative sign immediately, and there's no change to the cosine ratio at the end. So f of negative x gives you f of x, which is even. E-V E-N, there you go. Alright, before we get there, let's just real quickly do two things here. Let's go example 1. Can you give me sine of negative 30 degrees, and the directions are find the value using the even and odd properties. That's kind of what we want to do here. So because we know the fact that sine is a odd function, we change it to this. Easy enough. And because of that, we just say, oh, sine of 30 degrees is 1/2 with a negative in front of it. Boom. Okay, what this allows us to do really is to get everything back to a positive angle, or back even to quadrant 1. So that's kind of the help that we get here. Okay, how about B? Cosine of negative, let's see, 2 pi over 3. So cosine of negative 2 pi over 3. Cosine is an even function, so I can drop that immediately. I don't really even need to mess with it. So there, and then at this point I'm just looking on the unit circle at pi 2 pi over 3. That's in quadrant 2. And the x value is negative 1/2. That perfect. Okay, so it's not so much as that this guy's the negative, it's the fact that I was able to drop the negative sign and make it an easier problem for me. So let's go on to all the other trig functions here. So we got to figure out if it's even or odd. So tangent of negative theta. And remember, tangent is a ratio between sine and cosine. So all we're going to do, we're really just going to jump into this here, saying tangent is going to be sine of a negative angle over cosine of a negative angle. Remember, that corresponds to a negative y. Cosine of negative theta corresponds to positive x. So now we can kind of stick this little negative out in front. Ratio gets back to tangent, and voila, it's negative tangent. Even or odd? It already says it for you. It's an odd function. So if you drop a negative angle in tangent, you have to stick a negative on the outside. Cosecant, reciprocal of sine. And go for it here. So cosecant of negative theta becomes 1 over sine of negative theta. Again, changing it to coordinates allows you to have a negative in front of sine with a positive angle, but then that corresponds to a negative cosecant theta, which makes it an odd function. Moving on to secant, which is the reciprocal of cosine. Same exact process begins here. So 1 over cosine of negative theta. Since cosine is even, that gets to be dropped out. Back to secant, and we find out secant is an odd function. I'm sorry, even function. Even function. Cool. And last one, cotangent. Cotangent of negative theta, that's going to be the ratio of cosine to sine this time. And for cosine, it gets to be dropped out. For sine, it has to go in front. Move the negative on the outside, and the ratio becomes tangent once again. Oh, sorry, cotangent once again, but that proves it's an odd function. Okay, let's finish off the two problems here. So we did A and B, so this would be C. So secant of negative 240. If I'm doing this problem, I could drop the negative sign because it's an even function, and I just think about when is secant of 240. Secant of positive 240. I got to think back a little bit here, though, right? Don't I? Because then I think back and I say to myself, I got to think back what secant, what cosine is, right? So that's going to be cosine of 240. Cosine of 240, let me find it, is negative 1/2. Reciprocal of negative 1/2 is negative 2. So there's that. Alright, how about cosecant? Cosecant of negative 3 pi over 4. That's an odd function. Odd function, we have to stick a negative on the outside. That's going to be cosecant of positive 3 pi over 4. And again, a little bit of work to do there as well, right? That's going to be 1 over, we can put a minus sign right over here. Sine of 3 pi over 4. That's going to give me a negative 1 over the reciprocal of root 2, or according to our little that's that, which just becomes that right there. Reciprocal of 1 over root 2 just becomes root 2 with a negative in front. Alright, so hopefully that gave you enough of a understanding of 4.2 to go on with 4.1 in order to go on with 4.2 and 4.3.